In econometrics and financial studies, volatility is a much talked about concept. Now, volatility in a time series is a concept which is removed from what the Box-Jenkins models actually does. So, the Box-Jenkins models are primarily concerned with modeling the mean of a process, but what is seen in time series data related to finance and economic data is that there is much change in the variance over time. So, what we had been assuming in time series models or Box-Jenkins models in general, or even the classical models, was that we were assuming a constant variance, but this is very often violated in case of financial time series and economic time series as well. So, what we will be looking at in this and future lectures, next couple of lectures, would be the concept of volatility, what volatility is, how do you model volatility, and what the effects of volatility is. Let us look at a time series model and let us look at what volatility is in a time series. But before we come to volatility, let us look at the usual models that we have. So, yt is a time series and we observed this at times t equal to 0 to time t equal to n. Usually time series yt is modeled as mu t plus xt, and in this case xt is assumed to be the disturbance with expectation of xt equal to 0 and variance of xt equal to sigma square, which in most classical and Box-Jenkins models is assumed to be a constant. Expectation of yt therefore is equal to mu t, because expectation of xt is equal to 0. So, this is mu t for any t, and variance of yt is equal to sigma square for all t. So, the variance is independent of time. The covariance between yt plus h and yt is equal to gamma h for all t and any h. This is the condition of stationarity generally, that is the second moment is independent of time. Now, let us look at the components. What is mu t? Mu t is the smooth underlying process, and this is the smooth underlying process that we try to capture when we look at the classical models or when we look at the Box-Jenkins models. Whereas xt are the apparent irregularity in the process. So, usually in previous times they used to call this the noise. So, these are the irregularities. Okay. We will call it apparent irregularity because if we can later see that there are some patterns in this irregularity, and that is what we are going to capture. But for the time being, let us assume this to be an irregular component. Now, mu t can be viewed as the error free mean level along which the process evolves, whereas xt is the contamination. It can be positive or it can be negative, which makes the process yt deviate from the mean level. It is usually centered at 0, this xt. So, it has an expectation of 0, but it looks as if this is some sort of noise that actually makes the smooth process mu t irregular. Let us look at an example. On the left hand side we have the raw data, and if you look at the raw data here, you can see that the data is fluctuating and there are highs and lows in the data. So, what we do is on the right hand side we fit a model for mu t, and if you fit a good model for mu t, you get what is shown by the red line. So, the red line is a more or less smooth curve, it is a polynomial curve, which gives you a very good idea of how the series moves. But you can see the points do not all lie on the red line, because at each time point there will be some noises, and hence it will shift it away from the smoothness of the series. So, what we could have expected was that if there was no noise, then the series would be given by the red line. So, the deviations would be basically on the right hand panel, what you see is that the points are given by y t, the red line by the mu t's, and the deviations between the point and the red lines are the x t's, which are the irregularities. Let us make some observations here. The process mean therefore is modeled through mu t, which we have already seen. You see, expectation of y t is mu t. So, the process mean is modeled through mu t, while the process variability is modeled through x t. The variance of y t actually, because mu t becomes a constant, the variance of y t actually translates to the variability of x t, and therefore, the process variability is modeled through the x t component. What happened was that in early studies, both in the classical and the Box-Jenkins type of studies, the focus was on modeling of the mean, where the variance and covariances were assumed to be independent of time. So, we had used constant variance and covariances. As I said, the classical and Box-Jenkins models belong to this class of study. There it was only necessary to check for the mean stationarity of the process. Remember what stationarity means? Stationarity means that both the mean and the variance covariances are independent of time. That is the definition of weak stationarity. But since in the processes we are assuming that the variance is a constant, and hence the covariances also become constants, it really means that they are variance wise stationary. The variance is independent of time. But what we had been trying to do was that the mean was maybe non-stationary. So, we model the mean and then try and eliminate those and bring this down to a stationary process. This we have seen through modeling of the errors and the modeling of the trend and the seasonality components. So, let us look at an AR1 process. You have an AR1 process as y t is equal to alpha y t minus 1 plus epsilon t, where epsilon t is a white noise sequence with expectation of epsilon t equal to 0 and variance of epsilon t equal to sigma square. Notice that we are assuming the variance to be a constant sigma square. If you look closely at this model, then we can see that expectation of y t given y t minus 1 is alpha y t minus 1, and the variance of y t given y t minus 1 is equal to sigma square. So, let us pause here for a moment. If you compare this with what we have started with today, we said that y t was mu t plus x t. In this case, your mu t part is the alpha y t minus 1 part, and the x t part is the epsilon t part. So, x t is equal to epsilon t and mu t is equal to alpha y t minus 1. And if you are given the past, then the expected value of y t becomes equal to mu t, which is alpha y t minus 1, whereas the variance of y t given the y t values, past values, is equal to sigma square. So, it becomes the same as the variance of the epsilon t or the x t component. So, we can see that the mean is modeled through mu t and the variance actually depends on x t. So, this is what we had said before, that there are two components. One is the mu component which models the mean and the x component which models the variance. Unconditionally, however, expectation of y t is equal to 0, and if alpha is less than 1 in absolute value, for sufficiently large t, we have variance of y t is a constant sigma square by 1 minus alpha square, and we say that the process is stationary. So, why is the process stationary? Because we are modeling the mean out and then we are looking at the unconditional mean of yt, which is independent of time. And from the very beginning we have assumed that the variance is independent of time. Therefore, the process is stationary if alpha is less than 1. However, in most cases expectation of yt is equal to mu t, that is, it is a mean non-stationary process. In that case, what do you do? This is particularly true if there is trend or seasonality. Such non-stationary can be accounted for in two ways. Such non-stationarity means such mean non-stationarity. Firstly, what we can look at is the classical models. So, we usually the mean non-stationarity is caused by the trend and the seasonality. So, we estimate trend and seasonality and then eliminate the trend and seasonality, and this reduces the process from a non-stationary process to a stationary one. The other alternative is to look at the Box-Jenkins model. The usual Box-Jenkins model ARMA models are meant for stationary processes, but if you have non-stationarity in the mean, particularly because of trend, you can use the ARIMA model. If you have non-stationarity in the mean because of the seasonality condition, you have the SARIMA models. In fact, SARIMA models are meant for both the modeling both the mean non-stationarity in the presence of both trend and seasonality. So, the classical model and the Box-Jenkins models are primarily meant for modeling the mean non-stationarity. As opposed to this, what we have now discussed is that we have what is referred to as variance non-stationarity. Now, assume that expectation of x t is equal to mu. So, we have a mean stationary process. Mu can be equal to 0 also without loss of generality, because this is going to be a constant. So, unlike the yt's, the mu x t would have a constant mean. Engels suggested that a mean stationary series may exhibit different variability at different time points, makes the process variance non-stationary. So, what do you do? How do you get x t? You get x t by subtracting mu t from y t. So, y t minus mu t is equal to x t. Mu t was the mean non-stationarity component, and if you take that out from y t, you are left with x t, which is mean stationary. It may have a mean of 0 or a mean of some constant value, and in this case x t still may have some non-stationarity because of non-constant variances. We have assumed that the variance was constant for y t and x t, but if the variance for x t or for the exhibited series y t were not constant, then it translates to a variance of x t not being constant, and we say that we have a variance non-stationary sequence. This is particularly true for financial time series, where you have periods of hectic market activity, and that means that there is great fluctuation in the prices at those times, and then you have slack periods when you have stable prices, not much variability of prices over the days. So, there will be some greatly fluctuating prices and some times when you have very stable prices. So, we cannot say that the variance is constant, and we say that the process is volatile. So, volatility primarily means that you have variance non-stationarity. That means the variance is not constant over the whole process. Let us look at a series. If you look at the left hand side of the series, you can see that there are fluctuations, and the series broadly is initially going down, then it goes up, goes down slightly, and then moves up a little bit again. and there are crags everywhere. Okay. So, this is sort of oscillating around some value, small oscillations around some small central value. Now, if you take the mean out from this, so if you model the mean and take mu t out, mu t you can use a maybe in this case a polynomial, there are 1 maybe 3 turning points. So, you can use a 4-degree polynomial to model the trend, and if you take that out, subtract this mu t part from y t, you have the graph on the right hand side. You can see that the graph on the right hand side has a constant mean. So, it has leveled out, the mean has leveled out, but now you can observe that even then the process does not look to be quite random. You can see that initially there are very high fluctuations about the mean, and then somewhere in the middle these fluctuations become reasonably small, and then again it becomes high for quite a while, around 3/4 of the period, okay, and then finally it again becomes smaller. So, we can now say that the mean does not change, but there is a change in the variability, and we say that the process is volatile. So, even if you in the first diagram we had non-stationarity both in the mean and the variability. We modeled the mean, took out the mean non-stationarity part. So, it became mean stationary, but we can see that even if it is mean stationary, it can be variance non-stationary, and hence we call it a volatile series, and this is what actually we need to model. What is volatility? These are fluctuations in the series. Okay. It is a situation where the variability in this process is not stable or constant and keeps changing over time. So, the question is, will predictions be better if conditionally the variance is also modeled in the past? Mind you, we had modeled the mean conditionally, we had taken expectation of y t given y t minus 1, and that was alpha y t minus 1. Similarly, we can model the variance conditionally. Would it give us better results? That is the question. And Engel showed that it does give us better results, and he therefore postulated the autoregressive conditional heteroscedastic models. But before that, let us look at a few other models. So, how to model volatility? One alternative is to use exogenous information. What is meant by this? Suppose there is an exogenous variable which is not related to the current series. Let us call this W t, and we write x t as epsilon t into W t minus 1, where epsilon t is as before the white noise, or it has 0 mean and variance sigma square, and it is uncorrelated to the W part of it. Then expectation of x t is going to be 0, because expectation of epsilon t is 0. But if you look at the conditional variance of x t given x t minus 1, because the past is given, W t minus 1 is given, and hence that is a constant, and variance of epsilon t is sigma square. So, this variance becomes sigma square into W t minus 1, and therefore, the variance changes with time. So, it is not a constant variance over time. So, it is a changing variance depending on what the W value is at the t minus 1th time. The only problem with this model is that it does not evolve over time. That really means that the variance change is not related to the change in the process x t itself. The variance changes as W changes, not as x changes, and therefore, we say that it does not evolve over time with the process itself, and this is one reason why this is not such a popular model. The other reason is, of course, how to choose W. Let us look at a different alternative. These are the bilinear models. These are again quite popular. In this case, we write x t as epsilon t x t minus 1, And you can now see that in this case xt evolves with time because it depends on its own past value xt minus 1, and the epsilon t's again are white noises. This leads to variance of xt given xt minus 1 as sigma square xt minus 1 square. So, given the past values, the variance is sigma square into xt minus 1 square. So, in this case as xt changes, so does the variance of the next value. So, if xt minus 1 changes, then so does the variance of xt. So, we can have a variance which is non-constant over time, depends on what has happened in the past. But the problem with this model is unconditionally, if you take the unconditional variance now, it either becomes 0 or infinity, and that is a situation we would not like. So, that is one reason why this model is not as popular as the models that we are going to look at. So, neither of these two alternatives are very popular in the sense that one does not evolve with time, it needs an exogenous variable which can change differently, and the other has unconditionally a variance which is either 0 or infinity. So, the third alternative are the models that are proposed by Engel and later extended by other authors like Volatility. These are the arch and GARCH model. We look at an example of an arch model, an arch 1 model. It is given by xt is equal to epsilon t into sigma t, and we have sigma t square is equal to alpha naught plus alpha 1 xt minus 1 square. So, sigma t depends on the past values of x and xt depends on sigma t. Epsilon t's as before are white noise, but in this case we generally assume epsilon t's have a constant variance of 1. If you look at the expected value of xt given the past, this becomes equal to 0 because epsilon t has a expectation of 0, and again if you look at the variance of xt given the past, then this becomes alpha naught plus alpha 1 xt minus 1 square. This is sigma t square. So, you see the variance of xt given the past is now a function of the past itself, function of the last value. It changes as the series evolves. So, as the x values changes, the variance at each step changes. So, we have a changing variable model, and this arch and GARCH model has very nice properties as we will see later on, and hence are the more popular of the volatility models. So, what we have now is models which can account for changes in the variance as well. We need not assume constant variances. So, like what you did in regression, you started in regression with constant variances and then moved on to heteroscedastic models. The same thing we can do for time series as well. We started with constant variances, but then now we can change on to heteroscedastic situation where the variance is changing with time. In today's lecture, we have introduced the concept of volatility. Now, volatility really means that there is a change in the variance over time. So, unlike the mean modeling that we do in Box-Jenkins models, we need to model the variance in this case. So, how do you model the variance? There are several ways that you can do. You can use exogenous variable, you can use the bilinear models, but these models have their own problems. In 1982, as we saw, Engel suggested the arch models, the autoregressive conditional heteroscedastic models, and subsequently the GARCH models were introduced, and there has been a stupendous amount of work that has gone into the arch and GARCH models, and the literature now is heavily loaded with various types of or variants of the arch and GARCH models. We will look at those models in future lectures.